David Weise here, and you guys are watching Powertec 10. In this edition of Powertec 10, I'm going to reveal the latest phase of our development of our LS cam selection program. So this will give you a taste of what's to come. It's not finished yet. I think I've got a few odds and ends to work out with Stan, my partner in crime on this. But I think we've got the actual selection bit pretty much on the money. So let me show you what we've got. Well, here is our opening screen. See the mouse pointer going around over the screen? Well, the obvious first move is to hit enter. That brings us to this page here. Point I want to make here is note replacement performance engine parts. As you will see, we're not just showing you how to spec a cam here. We're going to show how this program specs the entire engine so that you have the best working combination your budget will allow. No other cam program and no other cam grinder currently does this. Right, we are going to have LSX, right? So we hit enter. These two don't apply because it's only hydraulic and solid roller cams. So we want a hydraulic roller lifter cam, and what we're going to do is go back to Eric Weingartner's cam test and see how well our new program with the exhaust features brought up to date, and see how close it is to predicting what the cam that won the challenge and what Brian Tooley's subsequent dyno tests showed. So here we go. We hit hydraulic roller lifter, right? And we go to enter, and that brings us to this screen here. We've got some numbers in here, but they're not anything to do with the LSX motor we're dealing with. So let's put in what we do have. First off, our 408 had a 4.03 bore. So 4.03 in, and a 4-inch stroke, 4 inches. Now, rod length is 6.098. Our valve diameter, that's the diameter in our AFR enforcer heads, is 2.08. Exhaust valve 1.6. The compression we're using here, as per Eric's 408 test engine with these heads, was 11.4. Now, what I'm doing here is I peak power RPM. The power range we had to work in was 4,000 to 7,000. Now, these LS engines hang on well on power, so our goal here is to give the best overall torque curve, not necessarily being 4,000 and 7,000, but because this is a strip motor, we want it to be able to run fairly normal streetable RPMs at low speeds. So what we're going to do is put in 6,750 for peak power. With the heads flowing as well as they do, we will be able to get to about 7.2 for a shift point, 6,750. Now, enter intended rocker, right, 1.7, and we got that there. Let's go back here, 1.7. Now, the reason it says enter intended rocker is if you have an option later on in the program, it will tell you what rocker you actually need, not what you wanted. Of course, if you're stuck with that rocker, that's it. You have to go with that rocker. But this gives you the option of knowing what rocker you should be using. So now we're going to go for a dual pattern cam. See, we got single pattern, put in a 0 here. Dual pattern, we put in a 1. Right, now I think we've got got to go over here. Induction length in inches. Well, we want 6,750. I've already fiddled around with this. We need a 10.87 induction length. That will tell us, and we're going to use the fourth reflection to get that. That's a bit of information I already knew. Now, when I hit this calculate button, I need to put in, it's going to be a street strip cam. When I hit this calculate data button, it's going to show us all this data in here from the lobe center line angle, 6 thousandths duration intake, 6 thousandths exhaust, etc. as you can read. It'll also tell you minimum intake and exhaust lift. Now, when we come to the idle vacuum, haven't got that quite sorted out yet, but I know where we've got to go with it. Dynamic compression, right? That's an important factor here. Cranking cylinder pressure, estimated torque potential, estimated power potential horsepower. Now, these power figures are assuming you build an engine that's top of the line for part selection and build procedure for the range that the engine's going to run in. For instance, if you're building a regular street motor, the program will look at the duration figures, figure out what RPM and it will take a model, a friction model and a pumping loss model that is applicable to that range of engine. So that affects these two numbers here, but it affects it in a way that reflects what you can expect. For instance, if we build a regular street motor, we're assuming that it's going to take about somewhere between 20 and 30 foot-pounds to turn the engine over, depending on the crank stroke and displacement and that. On the other hand, if we're building something like a pro stock motor, the bottom end torque number to rotate it may be as little as 9 or 10 foot-pounds. That's 20 horsepower difference, depending on whether it's a friction model for a road motor or a friction model for a pro stock or NASCAR engine. Anyway, it takes that into account. Now, let's hit this calculate data. Right, it's telling us minimum here. Idle vacuum's too low for a street strip. Well, we know it's too low. See, it's 8.6. That would be a small block Chevy one. We haven't got to changing that yet. Now, it says 408 is our cubic inches. Piston speed is 4,500. Now, you see these little red boxes here against these? Well, they have data. For instance, this red block here will tell you in the text how much piston speed with the parts you have is the max you can go to. Our target is to get between 8 and 8.2 in this box here for our dynamic compression ratio. Our cranking cylinder pressure we need to get to 200 to 210. We're looking at estimated torque potential 597, estimated power potential 687. Now those numbers are a little bit more than we saw in Eric's dyno test because the spec of the engine did not come up to what this one is supposing we could get with the highest spec possible. That we could get about 30 horsepower more and about 30 foot-pounds more with a full all-out spec than Eric was seeing on his engine, probably more than that. So these numbers actually turn out pretty good. Now, if you are not using the ultimate in intake and exhaust and carburation or fuel injection, you won't reach these numbers. But the next page is going to give you an idea of what you could reach, plus the information contained in the boxes. Now, this is pretty much done. Required minimum CFM head port flow, 338. Now, as it happens, our AFR heads that we're using are well in excess of that. Here's the target intake port CCs. Now, I haven't checked yet, but I don't know if that's right. But we'll look into that. But this is what we're concerned with here. Right, now the 10.87 gives us a tuned length requirement of 6,808, which is really close to our 6,750. We could just make that slightly bigger. I'll do that now. 688. Right, calculate 6,800. Let's go to 10.9. Or 10.92. Right. 6,777. That's close enough. No, we'll do it exact. Right. 10.9. 6,752 RPM with a 10.96 induction length. So if we had that, we'd have peak power there, peak torque there. Now we're going to street strip. If we'd have clipped these down here, we would have come up with a different specification. Now let's see what that does compared with the real cam. Right, it's 299, 315, much closer. In fact, it is far more reflecting Brian Tooley's cam testing than Eric's, because his engine was more precisely set up. So take a look at those numbers. That's what we need. And from here, we go to the Update Excel. And it takes us to Performance LSX Chevy hydraulic roller tappet cams. Some basic instructions here, answers will be going, but you already know that. Also, it is going to spec cylinder head selection, flow and port CC, springs, rockers, intake manifolds, spacers, carbs, EFI, cranks, rods, pistons, rings, etc. All on a cam program. Now, let's see where we go when we crank this up to the next line. Well, this is the next page. You'll see that it's got basic information up here. It says torque per cube is 1.46, horsepower per cube is 1.648. This is in foot-pounds per liter. Lobe center line angle. All this is from the chart just above, from what we got from our listing. But unlike most cam programs, now let me slide across here, let's have a look at some of the things that it exhibits. Not only does it give you the intake duration of a particular cam at 50, at 200, it gives the minor intensity, the major intensity, the intake lobe area, the intake lobe aggression, that is how aggressive the profile is, and we have numbers to show you the limits of that. Exhaust duration at 6, exhaust duration at 50, exhaust duration 200, intensity, etc. Lobe angle, lobe lift per degree, cam advance required, not just the generic 4 degrees, it actually computes what you need to have the cam set at from the flow figures and the exhaust sizes, etc. Required intake lobe center line, intake lift, exhaust lobe lift, rocker ratio, and this is where you can find out whether you've got the right one or not. Right? If you can't get the right one here with this will tell you what's the required lift. This will tell you what you've got. You can see that in this instance, and we haven't selected the real cam yet, but in this instance, it's not got enough lift, so it needs a cam lobe with more lift or more rocker. This profile here, profile series here, tells you 1, it's a street cam, 2, it's a hot street cam, 3, it's a street strip cam, 4, it is a basic race cam, 5, it's an all-out race cam. This tells you the springs that we've got, but we've got a spring program which goes with this spring at maximum lift, RPM limit, and it all ends up in the inevitable notes which tell you a little more about the profile and what it's good for. Now let me just demonstrate these little red boxes, right? Here's a useful one to go to. Put your deal on that there, and it says at the bottom, if the RPM entered for peak power produces a peak piston speed more than the following numbers, reduce the entered RPM until it conforms with the recommended limits. Now, following that below the pages, off the page, it will give you the rev limits for all the different types of materials and strokes of crankshaft, so that you can see you're not over revving your components. Let's look at another one here, vacuum at idle. Let's go to that one there. It's got quite a lot about that. This is the intake manifold vacuum that can be expected on an engine that it has excellent ring and valve seal along with optimal mixture and ignition timing calibration. In practice, this usually means an expertly set up fuel and ignition system. If there's any doubt that an optimal fuel and ignition setup will be achieved, lower the peak power RPM input so that a shorter cam with less overlap is spec'd out, or increase the compression if the fuel octane to be used will allow such. Now, this is all recommendations that help you, who probably isn't a pro stock engine builder, to know exactly what needs to be done. But there's more to go yet. Well, we've got this far in the video, and I've been working on it for over a week now. But one of the things I've realized through repeated playbacks for editing purposes is that editing wise it's very complicated, and it may seem like it's too, how shall I say, spotted with information all over the place. It's difficult to categorize it so that it's in a logical order, because it's almost like there is no logical order. So what I'm going to do here is go through and recap on what we've learned so far. So we'll start off with the basics, and that is the program allows you to select a cam. That's your starting point. Now let's say you don't actually have the right parts for it. Let's say that your cylinder heads, and you don't know this yet, have inadequate flow and inadequate port volume for the cam that you've picked. And how do you know this? Well, you go down and look at the CFM requirement and the port volume requirement. So you compare that with what you've got, and let us say that both of them are too small. So you've got several options here to make your power go. You can try all these to see how they come out, but what you can do is decrease the RPM at which the engine can attain peak power, right? And see if that suits what you've got. You can increase the compression ratio and see if it goes outside of the boundaries for the fuel octane you're using, but it will allow you to maximize the compression ratio. This means that you can use a slightly bigger camshaft at the same time. So that's an aspect there. But let's say you don't have any cylinder heads yet. Now, I know this is an unusual way to start an engine build, because most people start off by buying cylinder heads, right? Big buck outlay there. This program will allow you to select where you want peak power and then see what parts you need by investigating what heads are available, and the head section will allow you to go through about 200 cylinder heads and pick the one that's going to work best for your application. Now let's say you can't quite get it exact. You can go back to your cam selection and alter your cam selection slightly to suit the cylinder head, because that's the easiest way to go, right? Having a cylinder head ported just to suit the cam doesn't make sense unless you are a big buck engine builder. Now, you've now got an appropriate cylinder head for the camshaft. So now what's the next on the list? You need to have rockers. You now go and see what your rocker, your valve lift is, and select a rocker ratio which as closely as possible approaches what the program tells you. Now you may have already got some rockers and they only are 1.5s and it tells you you need 1.7s. How much power are you giving away? Probably around 20 to 25 horsepower, especially if it's a big motor. Valve lift on a big inch engine, and I'm talking about anything from 383 up, is going to be a big deal. Now of course this is an LS program and I just quoted you a small block Chevy deal there, but on an LS engine we're kind of in the same situation because we can get monster cubic inch displacements here. A 450 plus cubic inch engine is on the cards, and I've heard of guys building 500 inch ones. Lift. For something like that, you're going to need something in the 800 plus lift range. Be sure that you can actually build that kind of lift into the valve train for the applications you have. If you're doing a street application, you'd best have all the best stuff. Now let's move on another one here. We've now selected rockers, and that might be easy. You say, oh well, I just get this rocker here. Well, here's the unfortunate thing. The rockers aren't what they say on there. There is such a diversity in rockers that it's unbelievable. First, there's those that are fast off the seat, absolutely what you want for a big inch engine. And those that are lazy off the seat, absolutely what you don't want almost for any engine unless it's like a limousine engine. And you want it dead quiet and you want it to make 400 horsepower and you want it to run like a Cadillac. Right, so then once you've got the rockers, and you can go to springs, and in the spring section it lists hundreds of springs. What you do is you find out what you need for a seat preload and you isolate all of those with a button. Pick it. Now you've only got all the springs that are right for the right seat preload. That's often called seat pressure. It isn't seat pressure. Pressure is pounds a square inch. We need pounds. Pounds a square inch is in the tires. Pounds is the load. Just pounds. So seat pressure doesn't apply. It's seat preload. Okay, enough of my whining there. Now we go on to, I can't remember exactly what the next one is. I think it's manifolds. And it goes through about 100 manifolds, or maybe more than that, to find one that is either right for you as is with no more than a matching job and a cleanup, or ported. Finds the right manifold. But here's the next thing. It runs a far more, how shall I say, extensive program on selecting the best carburetor. And when you go through this program, you will see the carburetor isn't, well, I got this size engine, I want this much power to use, put this carb on. No. The carburation selection depends on whether you've got a spacer on or not, whether it's a single plane or two plane manifold. A two plane manifold requires more carburation per cube than a single plane. You'll see why. And if it's got a spacer on it, well, that carburetor could flow more air, so it requires a smaller space, and so on. So it goes through all of this. You won't find many carburation programs that are this detailed. So now you've got your carburetor. Then you find a crank for the engine. Then you find the rods. Then you find the pistons. Then you find distributor. So at the end of the day, this engine specs an engine out like you are a professional race car engine builder, even if this is the first engine you've ever attempted and you're 12 years old. Also, it allows you to select these parts without spending long evenings going through catalogs. For instance, once you know what cam you want, in the first stage. You can select, I'll show you how to select the cam in 90 seconds. That's barely any longer than it would take you to open so-and-so's cam catalog, and the cam may not be in there anyway. So that's what the program will do. So you will be building the best you can for the dollar you are prepared to spend. That's it. It's not parts you want, it's horsepower and torque, right? You don't actually want a camshaft, you want horsepower and torque. What by whatever means was necessary. If it's selecting a camshaft, let me say something here that I've said so many times. It's just as easy to select the wrong camshaft, just as price-wise the same, to grind the wrong camshaft, as it is to get the right one. Got that? And here's the thing. I've noticed that people who are less on a budget turn to companies that have off-the-shelf cams that are cheap. That's the worst way to go, because those cams are almost always wrong. So you have bought a cam, somebody who's not got a lot of money, that didn't buy you horsepower and torque like you hoped. So pay a little more for your camshaft and get one that's right, because like I said, you're not buying a cam, you're buying torque and horsepower. Got it? Now, on to our next deal. And it is a deal. I've got some parts to sell. Okay, enough of that. Let's go to our advertising section. Okay, our first item on the list. Set of Scat heavy duty rods for a 302. This is a 5.4 inch long rod. It was used for a build that showed only the build. So although it's been in an engine, it's never been run. Normally they are about, and this is a pretty bargain price for a rod like this. I've used these in a nitrous engine that was making about 1,000 horsepower. Didn't phase them at all. This was ages ago, probably 20 years ago now. So I can vouch for the fact that this is a heck of a rod, even if you're paying full Summit price, which is about $450. $200 plus shipping, and they're yours. Next item. Camshaft. Camshaft. It is for big block Chevy. It's a hydraulic roller tappet. What I would say is an advanced street deal. It's actually one of Terry's camshafts that he took a number of them after we tested this from comp cams. Not this cam, but that design of cam. And let me just pull this out here. I will read the specs for it. Glasses. It is 372 lobe lift. Lobe center line's 106. The duration at 50 is 230, 230. 274, 274. It's a hot street cam. Should have good all-round power. Will work wonderfully in a 496 or even slightly bigger, maybe up to about 520 inches, but 496 will work great. Anyway, these are around about $400 each from Summit. I will let this one go for $200 again. So that's it there. If you want to buy a hydraulic roller cam that really works, because you look, most of them are on something like 112, 114. They will give away 30 or 40 foot-pounds of torque compared with this. This will make your 496 into a street stomper. It will make more foot-pounds than most 540s will. 540s with the wrong cam in it, that is, and that's very commonly the case. So, $200 for that. And last on the list, I've got an intake manifold. Let me just get that. Now what we have here is a dart intake manifold. Basically, this was a prototype one that Dick Maskin of Dart and Pro Stop fame sent me to port and dyno test. He actually sent me 3. One that they'd ported, one for me to port, and one for me to saw up. Well, I never got to saw it up. I tested theirs, I tested mine, and for the same kind of port volume and port area, mine didn't make any more power than theirs did. So, hey, the only good thing is I was left with this manifold. Anyway, it works pretty good. Now, I gotta tell you, for one of them, the second one that we couldn't get any more out of, we tried opening this up to put an adapter on for a 4500 series carburetor. This one takes a 4150. It's a little lower than most manifolds, but higher than some. It's higher than the factory one by, I don't know, about a half an inch. It goes on a 10.2 block. The one that I ported worked very well with a 4150 1000 CFM HP carburetor on it, and it worked really good with a 1050 and an 1150 Dominator on. Our test engine, which was a 572, went right up to around about 800 horsepower, and it was street drivable. This was totally streetable. Only had a 9-to-1 compression. So, good manifold. Can you see this number here? $125. Now I should tell you one more thing that you need to know. It's a porter's manifold. In other words, the ports here are not finished. They are tapered from the length of my thumb or more down here to port match to whatever you want. So it does need working on, but if you follow my manifold story a couple of issues ago, you'll know exactly what to do to this. And in that form, you know, with these all rounded off, this knife edged, etc., it will do very well. $125 and it's yours. So where are we at now? I think what we need to do is to compare our computed results with the winner of Eric's shootout. And we'll do just that. So let's go to the page that's showing the end results. Here we go. Let's start at one of the most controversial numbers, i.e. the lobe centerline angle. Our program predicted 108, whereas the GPI or GP1, whichever it is, predicted 109, 1 degree out. Let me just make a point here. Having a cam 1 degree too tight on lobe centerline angle does not inflict any performance disadvantage. It does reduce the idle quality though. But 1 degree too loose can cost, on an engine of this displacement, 10, 12, 14 horsepower. That's what you'll pay for maybe another ½ inch of vacuum. Okay, on to the next step, duration. at least as far as the intake is concerned, it is only 1 degree different to Eric's shootout winner. Exhaust, however, at 315 is 7 degrees shorter. Now, you might think, so it's wrong by 7 degrees, but that may not be quite the case. The GP1, or I'm going to call it GP1 cam from now on, the GP1 cam was configured to win a shootout that was between 4,000 and 7,000. And as such, an extended exhaust would favor that upper RPM range. However, look at the torque of the GP1 cam at 4,000 compared with mine, and you'll see that my cam is probably, if I remember right, about 8-9 foot-pounds up. The reason for the shorter exhaust duration on this cam is A, to get a better vacuum. Now, since doing the start of this video, I've recomputed the vacuum numbers, and the small block Chevy and the LS engine respond to the characteristics of the cam in a very similar fashion. So what I've done is I've altered the program to take that into account at this point as far as a low vacuum is concerned. Now, you'll notice that the vacuum on the GP1 cam was 6 inches. The program predicts 8.6, which is right to the second decimal place as far as the calculations go, but it proves to be a very accurate deal. On the Chevrolet, the guys who are doing engines which have to conform to a vacuum say that the cam I spec out is very close to the vacuum limit, and they are applauding that because they can get the right cam for the job without having to flush several cams through in terms of finding out what the vacuum is. So our 315 is to cope with a power band from 2,000 to 7,000, not 4,000 to 7,000. And the thing is, if it's going to be a true street strip cam, it needs to have at least a reasonable streetability. So, exhaust slightly lower. What will we give up in terms of power? I'm going to make a guess. Probably close to nothing. How about what we get for average horsepower? A bunch more. So, if you were looking for a bit more horsepower, we could always just extend the duration of each of these lobes by just a couple of more degrees, and we get there. And just one last point on engine vacuum here. The biggest effect on vacuum reduction is brought about by the exhaust duration. Try this little experiment. Open up the intake lash by 5 thousandths on a solid cam and see how much it increases the vacuum. Not much. On the other hand, if you open up the exhaust lash by 5 thousandths, it will show a substantial increase in vacuum. Well, so far, so good. But we can't take the evidence we have now as being anything other than indicating we're going the right way. Now, fortunately, Eric and Brian have done some tests which are sufficiently different to the original tests on the 408. They did their tests on a 428. And so what we can see here is whether or not it predicts their cams relatively accurately. Now, the difference was that they tested several cams and they timed them in. So the tests were much more, looking for more accuracy and optimization. So that's where our next step will be. We will go there and see how the program, and I'll go through and still do some more stuff, will work out in, say, 2 weeks' time. Well, I think we've covered everything here, so let me say, please subscribe, like, and share. And if you've got any super thanks, that's great. So till next time, thank you for watching, and I'll see you soon.